Well, I have a lot of different topics, but what I'm really passionate about is the marine biogeochemistry and specifically trying to understand what we call that dissolved organic matter. It's a more general term than just looking at dissolved organic carbon. It contains also nitrogen compounds, sulfur compounds, and so forth. Interestingly, that material we don't understand very well. So if you take a sample from the deep ocean, try to look at the organic compounds in there, we can trace them to a specific extent, but on the molecular level, the structural level, we don't know it very well. So we really need to find out what this material really is.
What do you mean? Like what, in seawater or in estuaries?
So think about,
what kind of bodies of water are you looking at?
this is open ocean water. So we go out at sea and we take samples down from great depth. Deepest I got was from almost 5,000 meters. So that's 5 kilometers of cable going down with sampling bottles attached to it.
Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers, because once we do, we'll be able to put a donate button and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD, and working on a product to help people overcome these problems, because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you.
Forget frequently asked questions,
common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast, now part of the Finding Genius Foundation. I have Michael Gonsior. He's an associate professor, part of the Chesapeake Biological Laboratory at University of Maryland. We're going to talk about his research on the oceans and organic matter and plastics. So, Michael, thanks for coming.
Yeah, thank you for inviting me. I'm looking forward to talk to you.
If you would give me a little bit about background on yourself first, and then we'll get into the details of your current research.
Sure. Yeah, my background is in analytical chemistry, and then I also got a degree in engineering. But my passion was also always in water chemistry. So I went to get a PhD in marine biogeochemistry. So I went to New Zealand, did a lot of work there in the fjords and offshore, and then continued with a postdoc at UC Irvine in California for 2 years at the Urban Water Research Center, and then transitioned for a postdoc into Sweden, and again came back to the US, and everything else is history at the Chesapeake Biological Lab.
All right, well, tell me, what are some of the research questions you're working on right now?
Well, I have a lot of different topics, but what I'm really passionate about is the marine biogeochemistry and specifically trying to understand what we call that dissolved organic matter. It's a more general term than just looking at dissolved organic carbon. It contains also nitrogen compounds, sulfur compounds, and so forth. Interestingly, that material we don't understand very well. So if you take a sample from the deep ocean, try to look at the organic compounds in there, we can trace them to a specific extent, but on the molecular level, the structural level, we don't know it very well. So we really need to find out what this material really is.
What do you mean? Like what, in seawater or in estuaries?
So about,
what kind of bodies of water are you looking at?
This is open ocean water. So we go out at sea and we take samples down from great depth. Deepest I got was from almost 5,000 meters. So that's 5 kilometers of cable going down with sampling bottles attached to it. And then we take samples along depth profiles, and then we try to isolate the organic molecules out of that water, meaning its concentration is not that great, but overall, altogether in the entire oceans, the organic carbon content is as much as CO2 there is in the atmosphere. So it's a big pool of carbon, but it's very, very complex. So there are possibly 100,000, if not more, molecules, which we know about 20% what they are, but the rest, 80%, still remains unknown, the structural level.
I've interviewed quite a number of scientists on microplastics. Do you find them in seawater, and do you find them at depth? Have you looked at that at all?
Didn't look at depth, but I was involved early on in 2009 in the microplastic accumulation in the North Pacific. So we went out with a science team to look at that, and we did find, unfortunately, plastics everywhere, even at closer to the coastline. We went about 1,000 miles offshore, and we did find quite a bit of plastic. So yeah, we did achieve it that our imprint on the global ocean is occurring big time with plastics everywhere, mostly small pieces though.
Yeah. So what are you finding in the ocean? What kind of organic matter that, you literally can't identify it, or
yeah,
so because of the composition, it's very difficult? Like what's tough about it?
Yeah, so the sources are really algae and everything which fixes carbon. What does that mean? Carbon fixing means you're taking CO2, which is inorganic carbon, and turn it into algal biomass, and then the algae or the bacteria are going to die, and all this material, what they basically fix, going to be redissolved in the water, and then some of it is directly what we call mineralized, turned back to CO2, but some of it actually accumulates. And it is that is that large component of the marine carbon cycle, which we really don't have a good handle on what this is. So my research is focusing on linking what comes from those algal species and then ends up potentially in that undefined pool of organics in the ocean, specifically the deep ocean. There's some research from the 90s which suggested that material to be very old. There was some dating of the dissolved organic carbon, which basically what they found out that the deep ocean water in the Pacific is about 6,000 years old as the bulk measurement, and in the Atlantic a little younger. So they were claiming that it's a huge sink of carbon, obviously, if it's sequestered for thousands of years. But that question is coming into doubt because that assumed that we don't have sources of what we call C14-free or radiocarbon dead material. Think about oil, right? It's millions of years old. There is no radioactive C14 left because it's only produced by cosmic radiation in the atmosphere and then fixed within the living biomass, and then it starts to decay. But it decays, we can trace it up to about 50,000 years, but not longer. So when there is some material coming in which is older, then everything appears to be old, but it may not be old. It's only a small fraction. So there's a lot of debate going on now whether or not this material is really that old. So we have to kind of rethink about the age of the deep ocean pool of carbon in the big picture.
What age range could it be if it was quote unquote old or not old?
Yeah, that's a good question. That all depends on our budget of calculating how much C14-free material comes into the deep ocean from what we call seeps, oil seeps. There are plenty of them in the deep ocean at the seafloor where oil actually comes out of the ground. But there are also methane, right? Methane seeps around the world. There's also ancient CO2, which is actually, there are organisms which we call chemoautotrophs. What they actually do without the sun, they can transform inorganic carbon, meaning CO2, into also biomass and then into DOM ultimately. And what accumulates from them, it's really unknown. But they also, recent focus have shown that there is a substantial source coming from them, meaning they turn over about 1 gigaton of CO2 in the deep ocean. So that's quite a large number. If you think per year, and if you think about there are over 600 or 650,000, 660,000, well, 660 gigatons of carbon dissolved, and 1 gigaton per year, it's quite a bit. So, but they have been not used in budgeting the marine carbon cycle, so there's also some revision needed. So that it's a changing target, but it's hugely important because it's ultimately the least understood but most reactive pool of carbon on Earth.
Well, CO2 that's in the oceans, is there an active zone? And below that, the CO2 is pretty much inactive? Maybe the pressure is too high, there's not enough oxygen, et cetera?
Well, there's, of course, CO2 is fixed by algae, right? That's photosynthesis. Organisms take CO2 with sunlight and get energy out of it, and then release oxygen, right? But then also make biomass and then ultimately produce dissolved organic carbon. In the deep ocean, they also take in CO2, even at high pressure, at very, very low temperature. Think about the deep ocean having a temperature of 2 to 3 degrees Celsius. So now we're talking about 35, 36 degrees Fahrenheit. That's pretty cold, but they still thrive. So they still do it. They have other chemicals like nitrate and ammonia. It's the prerequisite to do it. And yeah, so they do it all throughout the whole entire water column. But the biggest, by far the biggest source is, of course, the surface ocean.
Has anyone tried to calculate a balance of transfer between the surface of all the water in the world, let's say, and the potential CO2 that would cycle between it and the air? Is that calculation possible or useful?
Yeah, there is definitely for the carbon cycle, it is useful. In terms of how much cycled through that dissolved organic carbon pool, there are estimates. Dennis Hansel, for example, at Miami Rosenstiel, then he did a lot of measurements around the world oceans, measuring dissolved organic carbon concentrations. And he came up with a number that is somewhere between 300 and 400 years to turn over the carbon, just based on the carbon budget. So that is an interesting number, but that's of course also a lot younger than the age of what we're measuring. So there's room for debate how we put that all together in an alternative way. At the moment, we're really thinking that the deep ocean DOC is very old and therefore inert, right? It's refractory. That's what we use as a term. It means it doesn't react anymore. It's hard to believe where you have a lot of bacteria around and oxygen that any reduced carbon going to survive thousands of years. I'm a chemist, so I have a hard time to believe that. So I think you can slow it down dramatically, but I don't think you can have a molecule which is based on carbon, hydrogen, oxygen, and other elements to be that old, any oxygenated world.
Before we continue, I've been personally funding the Finding Genius podcast for 4.5 years now, which has led to 2,700 plus interviews of clinicians, researchers, scientists, CEOs, and other amazing people who are working to advance science and improve our lives and our world. Even though this podcast gets 100,000 plus downloads a month, we need your help to reach hundreds of thousands more worldwide. Please visit findinggeniuspodcast.com and click on Support Us. We have 3 levels of membership from $10 to $49 a month, including perks such as the ability to see ahead in our interview calendar and ask questions of upcoming guests, transcripts of podcasts you're interested in, the ability to request specific topics or guests, and more. Visit findinggeniuspodcast.com and click Support Us today. Now back to the show.
What would happen? Let's say I drop a French fry into the deep ocean. What's gonna happen to it over the next 100 or 1,000 years? Or let's say a fish dies and sinks down to 10,000 feet.
There are a lot of bacteria in the ocean. They look for any kind of carbon to utilize. You can think of, right, if you leave your French fry laying on your table for a month, that doesn't look like a French fry anymore. So similarly, in the ocean, it's going to be degraded by microorganisms mostly, and then, ultimately turned into CO2. It's going to be mineralized.
Okay. So what are you trying to characterize? Like, have you identified a depth or additional layers in the ocean that have different activity levels? Like, what is the picture that's coming to you from your study?
Sure. The big question is about the turnover of that large dissolved organic carbon pool. How long is it really been around in the ocean? Is it really thousands of years or it's only hundreds of years? So the only way you get there is to find tracers which you have exact structures of a molecule. Then you can trace throughout the ocean, and therefore you can infer its reactivity. You can do experiments under pressure. You can look at different bacteria, how they utilize that specific compound and what they make out of it. But the dilemma is we don't have traces in the more stable pool of organic carbon. So my aim is really to find out some compounds that can do that. We have done experiments where we looked at a species is called Synechococcus. And there are two major strains in this world of those picocyanobacteria, they're called. They make out about 25% of the algal biomass in the ocean, so they're big players everywhere. And what we found out that they produce a fluorescent compound. So we know that produce a fluorescent compound which is stable at least over a month. We have now done experiments over a year and a half, and it's still stable in a world with bacteria there. So now we have a reasonably stable compound, which we still need to find out the structure, but because it's fluorescent, we're trying to figure out what that structure might be, so we can constrain it a little bit more. And another lead is where we looked at sargassum, which is that micro-brown algae which floats around the ocean, mostly known as a nuisance in the Caribbean, because it gunks up all those beaches when it ends up on the beach, and it decays pretty strongly, and then it smells quite badly. But it releases also a lot of dissolved organic carbon. It's amazing how much carbon is released by just one swimming plant alone. So there we can also trace where this material goes. That's another aim we were following.
Are you looking at biofilms that surround various materials at different depths as well? And if so, what are you finding?
We looked only at biofilms when we looked at more persistent material floating in the ocean, which comes back to the plastic, right? So there's a whole group which is outside of my part. I looked at more reactive oxygen species triggered by those biofilms, but what they found is there's quite a diverse group of microorganisms. They hitch along marine debris or plastics, and they even phrased a new term, the plastisphere, which means it's essentially the substrate is polymers which long live, and therefore they can distribute across the oceans much more so than before, because before, when they were clinging on any organic material, as we just talked about a French fry decaying on your table, similarly all the organic material or algae will die eventually and disintegrate, going to be mineralized. A part of it will turn into dissolved organic carbon of different reactivities, but the plastic flows around forever, and that biofilm there will be transported over large distances.
So are you characterizing, again, are you finding plastics at every depth that you're looking right now with your sampling, or are you ignoring that?
It's not like when we do sample water, we did find a piece of plastic in a few hundred meters depth once. Usually we don't find it in our small water samples we're taking. We're only taking 10-liter or 12-liter samples from any given depth. So this dispersion of plastics is much greater, that you would incredibly lucky in a way, or unlucky, if you want to phrase it that way, to catch one of those sinking plastics. But the ultimate fate is probably that even the plastic is going to sink. They become what we call negatively buoyant, so they're not floating anymore at the surface. And I've seen it happening even just in a beaker, because they're going to be overgrown by biofilms and other material, even by heavier material like clams and stuff like that, if it's larger material. And eventually it probably gets too heavy and it'll sink, and it will sink to the seafloor, which we have images. Some people have done some submersible work, some submarine work, where they found quite a lot of even larger pieces of plastic at the seafloor, where it's going to be sedimented. And in a way, it's probably a good sink for it if it gets out of the surface ocean, because it's more problematic by ingestion of animals and mammals by or birds in the surface ocean than it is when it gets buried in the sediments.
What kind of structure are you seeing in the seawater sampling you're doing? Is there any microstructure, again, like biofilms or the plastics plus biofilm, or other organic constructions that occur?
We're looking mostly in the dissolve. That means you don't really see it anymore, right? If something is dissolved, if you put a tablespoon of salt in the water and you mix it, that salt is gone. It's in a dissolved state. So it's not, when you do chemistry in a dissolved phase, it's not easy to see unless you have some material in there which have some interesting properties, like they absorb light strongly, or they fluoresce, so you can do them. You can actually see it sometimes, but no, it's not like it's easy to catch by eyes. That's chemistry is tricky in that regard. But what we can do, we can use analytical tools to make them visible. And I've been involved what we call ultra high resolution mass spectrometry, which is pretty interesting and rather novel technique to look at complex mixtures. Think about it, it's like a fingerprint of all the organics you can see through that lens, through that analytical window. And it's quite intriguing because it's mass spectrometry, so it's essentially measuring a very precise mass, but thousands of them at the same time.
So, again, with chemistry, a lot of the structure is not seeable with the naked eye, but possibly observable as a microstructures, or as you said, the chemistry itself will tell you about what's going on. Have you deduced any structure to the seawater samples you've taken at various depths? Does the chemistry change radically, as the pressure increases and maybe as the temperature drops, et cetera?
Yeah, we used a lot. A bulk parameter measurement with dissolved organic carbon, you can already see how much is there. We know there's a lot more in the surface ocean, a lot less at depth. So it's roughly half of the DLC in the deep ocean compared to the surface ocean. But then we use other techniques to look more at the fingerprint of the organic matter. In this slide, specifically ultra high resolution mass spectrometry. What is mass spectrometry? It's essentially measuring the exact mass of a molecule which is ionized. But you can see thousands of signals, and the technique is very interesting because it's so precise that the mass difference you can measure is less than an electron, and therefore you can actually assign an exact molecular formula. Think about it that you get thousands of signals which have an exact atomic ratios in each individual peak you're seeing, meaning you get a molecular formula. And that gives you a fingerprint. And we do see differences between the surface and at depth. There's, for example, much more organic sulfur compounds on the surface than at depth. We can also extract this material and do some interesting experiments with it. For example, we lysed Synechococcus, meaning algal DOM, in a pressurizer and then fed it just to bacteria and observed the changes of this material. And that was very intriguing because you can potentially find out specific organisms that grow at specific times during incubation, and they correlate with some specific molecular signatures. And those signatures you can further investigate and ultimately find out what their structure is. These kinds of approaches are going on in my research right now.
So what are some of the big questions that you're just not, you have hints of the answer to, but you can't tell yet in your seawater sampling?
Well, the big question for especially modeling big picture carbon cycle, even for the future climate, is really the reactivity of the overall pool of organic matter. But without knowing what the structure is, we can't do that effectively. So we're still in that realm that we need to find out what the structures are. We haven't gotten very far, unfortunately, yet. So this is ongoing research. There is some interesting hints towards very specific chemicals. One is actually based on a pigment from algae, from picocyanobacteria, which is called phycocyanobulin, and that breaks down in some interesting stable fluorescent compounds, which we're getting close, but not quite there. And it's probably not just one compound, it's a suite of compounds, but we can trace them. So that's great news for trying to get the first stable fluorophores discovered at the molecular level.
Have you been able to sample near any deep sea vents?
I have not personally sampled deep sea vents. We do actually have an analog on land. We do look at the hot springs in Yellowstone, but that gets us away from the marine environment, but it gets us towards more dissolved organic carbon, which may be old or coming from geogenic sources. Like in vents, we have about, depending on which vent you're talking about there, but the temperature can be very high. Similarly to the hot springs in Yellowstone, the source of the water is about 350 degrees Celsius, and that temperature, larger organic molecules want to be ripped into smaller pieces, and they recombine, and we don't know that process very well, but we can look at the molecular composition, what we're observing at the surface of a spring, and relate it back to potential chemical pathways.
Well, when you take a sample from, several thousand feet below the surface, how do you, you can't maintain the pressure on it. So how do you know when you get the sample up to the surface that it hasn't totally changed because of the abrupt decrease in pressure and temperature?
Sure. You definitely going to change the pressure, but think about that water is not affected by pressure, right? Gas is. So the pressure is still there when you go down there because there's a lot of gases involved, and the pressure, which is fatal for any humans if you don't have a pressure vessel around you. But the water is the system is quite genius in a way. You have tubes mounted on a metal frame, and then you have some sensors which tell you what depth you are. And those tubes are open at the top and the bottom, so water flows through them all the time. But then you have a trigger mechanism which releases a snapping in of caps at the bottom and at the top of those tubes. These called Niskin bottles. And what you can do, because you have the pressure sensors right mounted on them, you can actually trigger through an electric conducting wire at any depth, the bottles or the Niskin sampler. So then you trap that water at the depth you want, and then you bring it up. The water is still ice cold from down the depth when you have it at the surface. And then what we do in terms of chemistry, we do extract or isolate the organics, meaning we have 12 liters of water and then absorbing it to a specific resin and then getting it eluted with an organic solvent like methanol. And we're ending up with a 10 milliliter sample out of 10 liters, so that's manageable. Plus, we can concentrate.
And, and I interrupted you earlier. What other interesting compounds have you found that you're, just in the early stages of studying? What are the implications?
There is, I mentioned the seaweed or the brown algae sargassum before. They make an interesting pool of organic compounds. They're called fluorotannins. These are, if you take sargassum, put it in a jar, it's like tea colored within very short period of time. So it's incredibly visible in this regard. It's like, these are like, if you think about like a bog or any kind of lake which is deeply colored, this humic or this tannin color, you might remember walking through the woods and looking at the stream, similarly colored. And but they're very specific from brown algae. So we found out that there are a lot of them, hundreds of different compounds which have a similar core structure. And a few were known in the literature. We added a long list of potential other compounds in that pool. But there are also some interesting halogenated compounds. So these are brominated phenols. They are in there naturally. So often we think about halogenated compounds as being problematic, toxic. We talk about often in drinking water disinfection, making disinfection byproducts. They're usually chlorinated. If you have a little bromine in there, they're brominated. But these are bromophenols naturally produced by the sargassum, and we hope to trace those in the future as well. We just have the first depth profile on organic halogens through the ocean. 2 stations, one in the Atlantic, one in the Pacific, which shows also higher concentration at the surface and lower at depth. But we do know there's a large pool of organic halogens also in the deep ocean, interestingly, and this has been completely overlooked in the past because it's rather difficult to do analytically.
Oh, what about all the phage activity, that would surround the bacteria? I've heard there's just unbelievable amounts of viruses and phages in the ocean.
Yeah, that is an interesting subject when you talk about the viruses and marine virus research. I have a colleague, he's really working on this in detail. I collaborate with him. And specifically, there are cyanophages, for example. These are the viruses that affect the same algae I just talked about, those picocyanobacteria. And they effectively lyse cells in a very short period of time. So they're interesting in that regard to release those organics directly from the bacteria, from the cyanobacteria cells into the water, and then bacteria, heterotrophic bacteria, will take that material. But they do exist on other organisms, so it's still an active field of research. But viruses are a very important player in the dynamics of algal blooms and specifically the lysing of cells effectively when they get infected.
Is it? I mean, I would guess it'd be incredibly complex to model the chemistry. Is there such a thing as phage-assisted chemistry, or I'm sure there's bacterial-assisted chemistry, but what about phage? Is anyone studying that?
Yeah, it's the work done so far. It's really not driven by the chemistry of them, but rather by who's there and who's affected by whom. So it's more like the microbiology side of things. There is, not to my knowledge, any idea what phages are contributing to the dissolved organic carbon in a way. We know they are actually part of a very tiny pool of material in the deep ocean. In fact, they're so small that you can almost consider them within the dissolved organic carbon pool because it's practically defined. You just filter it through a small filter, and then the phage goes through, and they end up being analyzed with the truly dissolved organic carbon.
Deep down in the oceans, I mean, I would think that any processes that happen would happen very slowly. You know, it's very cold, high pressure, little to no sunlight. I would think there's very little exogenous inputs that would make the system change much over time. Like, what have you observed?
Yeah, that's the big question. How quickly are things turned over? You're right. Everything slows down. There is no light down there. We're talking about a few kilometers depth. There is absolutely no light. It's the abyssal ocean. It's the dark ocean. So light doesn't play a role, and temperature is so low that everything slows down. But not only that, the microbial communities change also. Now I'm getting a little bit out of my comfort zone in terms of chemistry, but what you see is a shift to more archaea, which are known to be growing very, very slowly. But again, the deep ocean is also the place where the chemoautotrophs thrive. These are the guys who take that CO2 and ammonia and nitrite and make biomass out of it. So they are there, and they are living there off those materials. So there is quite a lot going on. It's slower, but the question is what slow means. Because if it's days or weeks or months, that in the big picture is not very slow when you think about the DOC being currently understood to be thousands of years old. That may or may not be true, depending on what we're finding. So the turnover, what the bacteria are doing in the deep ocean, is incredibly important. And they're abundant. They're not like there's just a few. It's typically 10 to the 4th bacteria cell in the deep ocean, or 10 to the 5th, depending where you are. So it's not, there are a lot of bacteria there in a liter of water. I mean, a lot less than in the surface, but it's a lot going on at depth.
Yeah, I just thought it would be, again, slow, boring, quiet, not much happening. But I guess, like you said, there is still a lot going on.
Yeah.
Well, very good. Michael, what's the best way for people to learn more about your work? Where can they go?
Well, I mean, we do publish our papers, obviously. So we have actually a perspective paper we just published this year in Environmental Science and Technology. That's probably a good start to see what the current controversy is about the marine carbon cycling and the marine carbon turnover. They always can come to our webpage at the University of Maryland Center for Environmental Science. If they're really interested, they can also email me. We have a public email address, so I can be reached. But primarily we do publish in the primary literature and trying to advance the field. They are a little less accessible, but we do have also seminars for citizens, which are also public viewed, the Chesapeake Biological Lab, where at times we talk about the research going on in the different fields, so different gateways to get information.
Okay, well, very good. Michael, thank you for coming on the podcast. I appreciate it.
Yeah, thank you for having me, and Merry Christmas.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.